Hello, everybody. This is the third lecture on network science, in which we continue the discussion of some general definitions related to our subject, so applied graph theory, also called as network science. So, as a kind of rehearsal, we agreed that we are going to deal with graphs, and graphs are such a simple mathematical objects in which we have two sets: V, which is the set of nodes, and E is the set of edges, in which of course we have so an edge is a connected couple of nodes. And from here we can build up a wonderful modeling tool and a whole theory, which is called graph theory. And if it's applied for real life scenarios, then most of the times we like to call this as network science. So it was also mentioned last week and the week before that so network science has a very, very strong relationship with linear algebra, in which we have, the connection is made in such a way that a graph G can be associated with a matrix A. So let me, matrix A. Well, this matrix is called adjacency matrix. And of course, there are other matrices as well. Last week we saw one of them for the bipartite graphs. So, but a very natural, let's say, correspondence between a graph and matrices is the concept of adjacency matrix. Now, you remember the definition, so I don't want to repeat, but that is actually a very interesting scenario, because one is wondering, or we are wondering actually, if we can write down, or if we can state all the theorems in graph theory in the language of linear algebra. And it could be also working in a backward way, so all the theorems and all the constructions and algorithms which you can build up with linear algebra, they should have a meaning in graph theory. And apparently it happens that there are lots of concepts in graph theory or network science which has natural description or natural write up, or how to say this, but you know what I mean. So a natural way to express that thing in linear algebra, and vice versa. But maybe not all. So that would be maybe a bold claim, although it's claimed actually by some people that all the theorems, everything which is in graph theory, it has applicable translation, let's say, to linear algebra, and from linear algebra you can get back to graph theory for in every case. I'm not sure about it, but that's just a matter of knowledge. Okay, so let's see what we have for today. So maybe I should make this one smaller. Okay, so we covered all these definitions already, and I think we ended up with the planar network. So let's continue with the next definition, which is the degree. Okay, now of course this so degree is a really fundamental definition in graph theory, and as such it has a very natural interpretation also in linear algebra. So the degree of a graph, degree of a node. So degree is is well, is a function basically which takes the nodes v, the set of nodes, and then it assigns, well, a natural number including the zero, of course. But okay, so in my opinion, actually, natural numbers contain the set of natural numbers contain zero. But let me put it this way. So of course, if we have a small graph like this one here, maybe then of course you know the definition of the degree. So it's the degree of a node is the number of edges it is connected to. So for this node, the degree is equal to 2. For this node, degree is equal to 2. For this one is 1, and this one is 3. And maybe I can put here a separated node for which we have, of course, the degree equal to 0. Now, if we check the slides, then we can see that here the definition is given with the usage of the adjacency matrix. And you can see that actually what happens is that we take the adjacency matrix, which is always a square matrix, okay? And then it says that for a certain fixed row I, so this should be row I, we should let it run the second index, which is regarding, so that's the second index, so that's the column index, of course. Sorry, column. So that's the column index. So actually what happens here is that we sum up all the numbers which are in row I, okay? And that's going to be the degree. That's going to be the degree. Now, in this case, for simplicity, we assume that here we have either 1 or 0, okay, ones and zeros. Of course, the whole concept works also for weighted graphs. So if we have such a graph in which the edges are weighted, then this concept of summing the row in the adjacency matrix also works. Okay, so that with that you get the weighted, the so-called weighted degree. So that's actually a nice thing, because it really seems that we can very easily calculate the degree of the nodes. Okay, now you can see it clearly that actually if we have an undirected network, so undirected networks, let's assume that that the number of edges is equal to m. Okay, so the cardinality of the set E is equal to m. Now it's also easy to see that in that case we get this equation here, which comes from the fact that if we do, so I mean, just getting back to this matrix. So now if we do a row sum, then we get a number here. Okay, that's going to be the sum of the ones in, okay, assume that we have now an unweighted graph. So then in this row, then we also get a number, this row we also get a number, and so on. So basically what we get here as a row, as a sum of all the rows is a vector which contains all the numbers in which are, so the sum of the ones in the corresponding row. Okay, now please note that that the matrix which we have, this matrix A, is symmetric, which means that the transpose of it is equal to the matrix itself. The transpose can be obtained by just so in A transpose, the element A Ji is equal to A I J. Okay, so That's the symmetric matrix. So if we add up all the numbers in the matrix, then we get 2 times m. That's obvious, right? And it's equal also to these numbers here. The sum of, so this is going to be equal to k sub I, okay? Then this is going to be equal to k sub I plus 1, and so on, and so forth. So if we sum up all these k sub i's, then we get all the edges multiplied with 2, because every edge is counted twice because of the undirectedness. And hence we can divide the equation with 2. So then what we get is m equal to 1 over 2, so half of the sum of all the degrees, which can be rewritten also in such a way that the half of the sum of all the elements in the matrix, of course. So that's nothing surprising. But what is nice from here is that we can obtain also very easily the average degree of a network, which now the average degree, maybe we can denote it as average degree. Okay, just yeah, this is a stupid notion, but let it be like that. So well, what it does then, it takes the whole graph G, okay, and it assigns well, maybe a real number to it. So I just wanted to somehow hint you that degree, as it was written here on the notes, that's a local kind of measure. Okay, so it assigns a natural number to all the nodes, whereas this one, the average degree, is some kind of global number, global measure, which assigns a real number to the whole graph, to the entire graph. So it basically characterizes the graph with one number. Okay, and how do we calculate it? Yeah, obviously we sum all the degrees and then we divide it by n. That's it. And given the fact that yeah, so getting back to here, so you see m is equal to, I mean, this is nothing else but 1 over n, sorry, 1 over n, and then you see the sum of ki's is equal to 2 times m. Okay, so basically this is what we get here downstairs. So the average degree can always be calculated. That's the message. So the average degree can always be calculated without visiting the nodes. Okay, the only thing we need to know is the cardinality of the node set and the cardinality of the edge set, and then we can calculate the average degree with 2m divided by n. Okay, the next thing is density. That's also a global measure, which means with this global measure as an expression that it assigns one number to the entire graph. Okay, and this is the letter here is called rho. Okay, and this is the density, and the density, what it does is it divides the number of edges with n choose 2. Okay, so this one here, n choose 2, is well, that's the number of edges in the complete graph. Okay, so this is the amount of edges we can have in the complete graph. Amount of edges in a complete graph with n nodes. Okay, So if we have n nodes and then we form a complete graph in which, so a complete graph is such a graph in which all the nodes are connected with each other. Okay, then we have this amount of edges. Now, of course, n choose 2 has this. So it's just a notation. I think it's n factorial divided by 2 factorial and multiplied with n minus 2 factorial. Okay, so with that, what we have, okay, where should I continue? So that means that we have here, if this is equal to, okay, where should I, maybe here at the bottom. So that is going to be n multiplied with n minus 1. So we can, of course, simplify with n minus 2 factorial, and is divided by 2. So that's going to be the number. And you see, this is why we have this one as a continuation of the simplified version of the formula before. So it's 2 times m divided by n times n minus 1. And now we can have 2m divided by n, which is the average degree, and is denoted by c. So it's the density is again is equal to the average degree divided by n minus 1. So note that we can calculate the density again without visiting the nodes. Okay, the only thing we need to know is the number of nodes and the number of edges, and then we can calculate immediately the density of a graph. Now, a density, of course, is a number between 0 and 1, I guess, and so the dense networks, okay, those in which we have lots of edges, usually the density is a relatively large number, but we can also say that if the graph is kind of growing, so let's say it's a dynamically changing network in such a way that it's growing, then if the density remains to be constant, then we might want to call the network as a dense network. And with the growing network, if the density tends to 0, then that's an indication definitely of a sparse network. Now, for example, the World Wide Web is supposed to be a sparse network. But for example, the friendship network, we can also call it sparse. But it's also an interesting thing to think about, that still the friendship network, even if the graph itself is growing, then usually the number, so I mean, what is maybe also written here on the slide is that let's assume that there is a group of people, and then we form the friendship network in it. So then 2 people are connected if they are friends, okay? And then let's say that then some other people are joining to this group. Then most of the cases, what happens is that the number of friends don't change, okay? So we can maybe put it even more radically, that given the fact that, well, maybe like 100 years ago, the population on the entire Earth was maybe half of the current one, or maybe even less than half. Still, the number of friends among the people on Earth don't really change, okay, over the time. So it remains kind of constant. Still, the friendship network could be called as a sparse network. Okay. So for directed networks, The degree then becomes an interesting thing, because then we need to count, we need to distinguish the in degree and the out degree. Okay, so of course, if we have a graph like this, again, then if we have some kind of direction, like, oppa, sorry about that one, I pushed it accidentally. So if we have a direction, let's say this kind of direction, then of course this has out degree 1 and in degree 1. This has out degree 2 and in degree 0. This has out degree 0, in degree 2, and then 0 out degree and in degree 1. I hope that the first one was always the out degree and the second one was the in degree. Okay, so now we get a kind of different picture than before, and now you can see that that a node can have very easily can have 0 in or out degree. Still, the graph as an undirected graph can be still connected, okay, as an undirected one. Okay, and the definition is simple, because you can see that the in degree is what it says is that it's basically a row sum, and the out degree is this one, and this, in this case now, the running index is the first one, so this is going to be a column sum. Okay, so what I mean with row sum and column sum, so maybe the column sum I can demonstrate here, that it says that one of the columns, j, is fixed, and then the running index goes through the elements in that row. Sorry, that that column. Okay, and from here, it's also true that the average degree is half of the degree of the half of the average degree for the half of the average degree if the graph was undirected. Okay, so the next topic is paths. Now, path, as we introduced it last week, is a route across the network that runs from vertex to vertex along edges of the network. Okay, this was explained in the previous lecture. Now, what wasn't mentioned perhaps is that it can be directed or indirected, and well, of course, it makes sense to consider the path length as a number, and it's the number of edges in the path. Okay, so it's not the number of nodes, but it's the number of edges. So we can also want to call it number of jumps. Okay, so it turns out that actually, and this is pure linear algebra. Okay, so if we want to have the path of length r from node I to node j, then what we need to do is we need to take the matrix, the adjacency matrix, okay, power it, so like raise it to the power r, and then see the entry at row I and column j. Okay, that's going to be the indication of a path between I and j which has length r. Okay, now if you think about it, if r is equal to 1, then it's funny, because then it means that we are looking for a path of length 1. Okay, so length 1 paths are actually nothing else but the edges in the graph. Okay, so obviously the adjacency matrix raised to the power 1 is the adjacency matrix itself. So of course the entries I and j, we have 1 there if we have an edge So by definition, this is true. So R equal to 2, that's going to be 8. So the matrix is multiplied with itself. And so this means that we have a non-zero number at row I and column j if we have a path from node I to node j, whatever it is, okay? And a path of length 2, okay? It doesn't matter which way it goes, but the length of the path is equal to 2. Right, and then apparently it turns out that if we raise it to the rth power, then we get a non-zero number at entry I and j if we have a path of length r between node I and j in the original graph. So that's really amazing. And from here, we can introduce a notation which is L sub r, and that could be that notation means the total number of loops of length r anywhere in the network. Okay, loop should be replaced with cycle, as we said last week. So that was the thing, that we have a graph, and then we start from a node, and then we visit another one, and then sooner or later we get back to the same node. Okay, so this is a cycle or loop of length r in our network. And apparently it turns out that the diagonal entries in our adjacency matrix raised to the power of r gives the total number of cycles in the network. Okay, I mean, of course, if we have 5, then the total number of cycles, including node 5 in the network. Okay, and this TR is just a notation that is called trace of a matrix, and you can see that by definition the trace is nothing else but the sum of the diagonal elements in the matrix. Okay, so that's just a notation. And so the path can be considered so symmetric adjacency matrix or unsymmetric adjacency matrix. So if a network is undirected, then of course A is a symmetric graph. Now, well, with a bit of a linear algebra, just if you don't get this slide, then don't worry about it. It's just a nice fact that LR it was actually equal to the trace of the adjacency matrix raised to the power of r. Okay, and then apparently if A is symmetric, then we can have this kind of decomposition of our matrix with two matrices, U and K. U is an orthogonal matrix and K is a diagonal matrix. Okay, so a diagonal matrix contains only elements in the main diagonal and everywhere else is 0. And an orthogonal matrix has this property. Orthogonal matrix has this property that the U transpose multiplied with U is equal to the identity matrix. Okay, this is going to be used here. All right. So so there is a decomposition of a symmetric matrix into this form. Okay, by linear algebra. Okay. So then we can write, instead of A, we can write U times K to the power of R multiplied with U transpose. Now, it's also true that U R, if U was orthogonal, then it's equal to U. Okay? And then yeah, maybe this is not true, but sorry. So maybe I should remove this one, but it's definitely true if we take the trace, okay? So then we can even rearrange the multiplication inside the trace function, and so this is going to be the identity matrix, and this means that we need to calculate the trace of the matrix K raised to the power of R, and apparently it turns out that K in this decomposition is such a matrix in which the diagonal elements are equal to the eigenvalues of the matrix A. Okay, so in this lecture, the eigenvalues are denoted with kappa. Okay, so for kappa, it holds that A times x is equal to kappa times x. So that's where x is a non-zero vector. So that's the so-called eigenvalue-eigenvector problem. And well, this is nothing else, just a serious linear algebra, which says that that the number of the number of cycles in our network is equal to the of length r, cycles of length r, the number of them, is equal to the sum of the eigenvalues of our adjacency matrix raised to the power of r. Okay, amazing. Similar property holds for the directed networks. Okay, I'm not going to explain this slide, but you can see that the derivation results in the same fact. Okay, so don't worry about these 2 slides or 3. This was just a simple demonstration and brief, not detailed demonstration of the fact that there is a very nice and very strong relationship between certain graph properties and concepts or properties, linear algebraic properties of the corresponding adjacency matrix. Okay, now the shortest path and the related stuff is going to be explained in the second video of today's lecture.